Good afternoon, everyone. We are Group 150. I'm Madhuri and I'm joined by my teammates Vaibhav and Devesh. And today I'll be presenting our final project titled Advanced Neural Networks for Diabetes Prediction. So, moving ahead, diabetes contributes to a significant global health concern and it contributes to a long term complication and healthcare costs. So, early detection plays a vital role in reducing these impacts by enabling timely treatment and also preventive care. And we all know that traditional diagnostic methods are often expensive and not scalable in low resource settings. So, hence, our goal here was to build a machine learning model which is capable of accurately predicting diabetes using basic health indicators, allowing for faster and more accessible risk assessment. So, moving ahead, here's our data source. We use the PIMA Indians Diabetes dataset, which is publicly available through Kaggle and the UCI Machine Learning repository. So, this dataset contains medical records for 768 patients aged 21 or older, and each record includes 8 clinical features such as glucose level, BMI, insulin, etc., and also a binary outcome indicating whether the individual was diagnosed with diabetes or not. So here's our pipeline overview. After cleaning the data, we standardized all feature values using the standard scalar to ensure consistent input distributions for the model. And also to address the issue of class imbalance, with diabetic patients representing only about 35% of the data set, we applied SMOTE or synthetic minority oversampling technique, and it generates new synthetic examples of the minority class during training, allowing the model to learn from both classes more evenly. And we then performed an 80-20 train test split, ensuring that both sets retain the original class distribution. So moving ahead to our ANN architecture, it was designed to process structured tabular data effectively, and it accepts 8 input features, such as each corresponding to one of the normalized clinical indicators. And this model consists of 3 fully connected hidden layers, with each layer followed by batch normalization, ReLU activation, and dropout. So, batch normalization improves training stability and convergence speed, while dropout helps prevent overfitting by randomly deactivating neurons during training. And our final layer, it's a single linear neuron without a sigmoid function because we incorporated a custom loss function. So specifically, we used adaptive focal loss with a gamma value of 2.5, and this loss function shifts focus towards harder to classify diabetic cases, which helps improve recall and model robustness. So moving ahead, here's our final results. So once trained, our model demonstrated strong performance across all metrics. And on the test set, we achieved an overall accuracy of 89.4%. And more importantly, we reached a precision of 85% and a recall of 90% for the diabetes class. And this resulted in an F1 score of 0.87. And these metrics indicate that the model is both accurate and reliable in identifying diabetic patients, which is essential in medical screening applications. So, moving to the next slide, here's our graphs, and these two graphs show how our model improved over time during training. So, on the left, we see that the training loss continuously decreases, which means that the model is learning to make better predictions on the training data. And on the right, we see that the validation accuracy steadily improves and reaches about 90% by the final epoch. And the consistency between low training loss and rising validation accuracy indicates that our model is not overfitting and generalizes well to unseen data. So, moving ahead, we are comparing our ANN model with our random forest model, which we use for our baseline. And to compare, the random forest model achieved only 64.3% accuracy with a precision of 50% and a recall of 52.7 for the diabetes class. In contrast, our ANN model significantly outperformed these metrics, demonstrating the impact of our neural architecture, proper class balancing using SMOTE, and specialized loss functions. So we also explored using CNN, but their performance was limited because CNNs are better for image of spatial data and not for structured tabular data sets like ours. So that's the results, and here's our team contributions. It was a collaborative effort, and Devesh worked on establishing the baseline models and optimizing our evaluation metrics, and Weber focused on data pre-processing and EDA. And I led the design for the model architecture and managed the training and tuning processes. So moving ahead, yeah, here are the references, and these provided us with both practical datasets and valuable insights on the model architecture, training strategies, and evaluation metrics used in prior work. So that's it, and that's the end of our presentation, and thank you for your time.